So hello everyone. Today we'll build some models using scikit-learn. So before we start, by the count of hands, who has never used pandas or numpy before? Just, I guess everyone has used it, right? No? Yes. You used it, right? Yeah. So this notebook assumes that users have some prior experience with numpys and pandas. I mean, if you don't know something about some functions, you can go back and then play around with it. So first of all, we need to load the packages. This is a good practice so that your next people that will be using the notebook will know what packages they'll need to use that notebook. Yeah, so let's load it. And here we'll need pandas, numpy, matplotlib, seaborn, and scikit-learn. So first of all, we'll build a linear regression model. Let's start with something simple. So we have the CSV file, and basically it has a data set with 101 observations. And there are 4 attributes, 4 features that are time, gender, height, and shoe size. So we'll be trying to predict shoe size based on gender and height. So first of all, let's load our data set. So here we're loading the data set, and we can also print out some useful information like first 5 rows, summary statistics, and whether there are null values and where they are. And we can also plot our data set. And just by looking at this information, can anyone tell me what data preprocessing we might need here? Yeah, just by looking at this. What do you guys think? Like, what preprocessing our data could use here? Yeah, so outliers, right? Yeah, so as you can see, there are some outliers here. I mean, we don't automatically remove them because maybe it's just, maybe you don't have enough observations and it's just, it looks like an outlier. But here, of course, there are no people with height of 350 centimeters, right? 3.5 meters and 0 meters. And so, of course, we can remove it. What else?
Can change the dimensionality of the.
I mean, you don't need to change dimensionality, but there are some missing values here, right? Yeah, so we have to deal with them, of course. And also looking at here, what could we do here? First of all, time. Do we even need this predictor or feature? I mean, it's not predictive, right? We could just remove it. Yeah, that's just time when the observation was recorded. And what about this variable?
We need to change it into the binary form.
Yes, so
numerical.
Yeah, so this is a categorical, right?
Yeah.
And then there are 2 labels, woman and man. So we have to create dummy variables.
Yeah.
So perfect. Yeah. So let's do that. So at this. So first of all, let's remove our time feature. So we can do that using ilog function. So I'm just redefining this data set. I'm saying data set is each row and then column 1 to the end. So I'm removing the index 0 column. And as you can see, we don't have it anymore. And if someone hasn't used Jupyter notebooks or Colab before, you don't have to print the last line. It just prints the last line for you. Yeah, so the next step will be removing missing values or dealing with them. We can do that using this code. IsNull just finds whether it just checks whether a row has a missing value or not. Yeah, so we can just print out a row which has a missing value. And here you can see the row with an index of 85 as a missing value. And I mean, it doesn't have any information, right? I mean, if you have a missing value, what you can do with it? you can either impute it using some information you have there. You can just try to guess what the missing value is, or you can just drop it. Here we only have one row missing, so we can safely, drop it. And also, I mean, it has no information, so we have to drop it. So we dropped it. Now let's just verify that we have no more missing values left. And yes, as you can see, there are 0 missing values now. And also now we have to deal with outliers. So here what I'm doing is basically I'm finding everything in a data set, each row that has height less than 30. Yes, and this is height, right? Yeah, and then also height more than 210. I mean, these are the outliers. And as you can see, there are some recordings with height of 184, 163, 361. I mean, these are just impossible recordings. You can try to guess and like fix it, for example, but here you cannot do that because height, I mean, okay, it might be 10 millimeters, 100 millimeters. I mean, it just doesn't sound real. And it's only 5 rows, so we can just drop it. But normally you would want to fix it because we only have 101 observations, right? Yeah, so let's do that. Let's run this one. Yeah, so this is OR operator here. So I'm finding everything less than 30 or more than 210. But then I'm dropping using AND operator. I'm just saying, so yeah, more just keep everything more than 30 and less than 210 at the same time. Yeah. So now we can visualize our data set. I'm using matplotlib to do so. Yes, so basically, as you can see, I mean, what you can see from this plot. So basically, it makes sense that like male. Oh, I think I switched colors here, but male has like a bigger height and bigger shoe size. I think I switched colors here for legends. Yes, so the next step was creating dummy variables, right? We also call it one-hot encoding. So we had this feature that was called gender, sex, and it had male, female, or man, women. And so we'll create this new feature that's called isMale. And we can do that by using pandas get dummies function. And it will create us this new feature. Do we need to keep like is man and then is woman or not? No, right? Because from this you can know like whether it's a woman or not. Normally, if you have 3 categories, 3 labels, you only keep 2. So normally you drop the last one because normally we don't want our features to be correlated. Some models cannot deal with highly correlated predictors, so we just drop one of them. Yes, so now, I mean, as you've seen, we've done a bunch of stuff to preprocess our data, and then you'll see how few lines of code it will take us to train model itself. So first of all, we'll split our data set into train and test set. And here, I mean, you can look at this code. It's from scikit-learn. And here we just need to specify our X, our Y, right? Our labels, our features, and a test size. We're just using a test size of 20%. Random state, we need to use random state for repeatability. So each time our random numbers will be the same. And also where I'm using a stratify here. So basically in stratify, so I'll go back to here. So as you can see, like the proportion is not the same, right? Like there are many more females than males here. And for example, if we don't use the stratify function, if we don't use this stratify, our test set and train set will be different. We'll have different proportions of males and females. But if we want to keep it the same, we can use the stratify option, and it will just keep it the same, keep proportions the same in both train and test set. Yes, so and also here, I mean, to build the model itself, first we need to define it. We're using linear regression model. Yeah, set fit intercept to true. Then we use linear regression fit to train the model itself. We're training it on the test on the train set. So for that, we need to specify X train and Y train. And also we can print coefficients here and intercept. After we build our model, we'll predict it on the on the test set, and we'll call it Y hat. So Y hat is basically our predictions on X test. And for that, after that, we'll calculate mean square error and R square. Normally, you just want to have one metric, because what if one model has better R square, but then worse mean square error? I mean, you cannot really choose, right? So before you build your models, normally you choose one metric, like one ground truth. But just for you guys to know and like to see, I just printed out two metrics. Yes. So let's see. So as you can see, these are our coefficients, right? We also always want to confirm sizes of our train and test set just to be sure that everything is right. So there are 76 observations in the training set and then 19 in the test set. These are our coefficients and intercept. Because we have two features, right? I mean, it makes sense. We have two features, and there is a coefficient for each feature, and then there is that bias term. Now we use our test set to test our model. So it has a mean score of 165 and R score of 0.81. So basically, I mean, you can if you're looking at R score, it means that 81% of variability of our Y can be explained by our features. So I mean, it's pretty good.
Why are you taking two errors? I mean, R square and then MSC?
Yeah, normally you just choose one. I'm just showing you that like you can choose whichever.
But it's like so different.
Yeah, they are different. They just mean different things. Mean square error, basically, your loss function is square error, right? So this is mean square error. What's the difference is? You cannot really tell. I mean, if you have two different data sets, it's really hard to compare your mean square errors. Yeah, so it's hard to interpret it. But then R square is easier to interpret it, but normally people use mean square error. It's just more reliable. But R square just means that percent of variability, in our case, 81% of variability in our Y, in our labels, can be explained by your features. So these features are explaining that much of variability. Because I mean, if you want to build a perfect model, if you can capture each predictor, each feature that can explain this model, I mean, it will be perfect, right? It will not be stochastic, it will work perfectly. But here, these features, basically, it means that your shoe size for 85% can be explained by your height and by your gender, and at least for this data set. Yeah, so let's visualize it. We're using matplotlib again. I'm not sure whether it's which. Yeah, again, these colors, legends, I have to change it. But you see, I mean, this is male, this is female. And what's interesting here is that you have two lines, right? Why is that? Why is that? Why do we have two lines? I mean, normally linear regression just puts one line, right? Why do we have two lines? Yeah, so it's one for each. So basically we have two coefficients, but then we're also saying, is it male or female? If it's female, the value itself will be 0, right? So coefficient won't matter. So it will go slightly lower, and then the slope will also be slightly different. So it's automatic. I mean, we didn't build two models, but then we have two lines, right? So this is how our binary variable is helping us to make our model more flexible. So second example, the first one was supervised regression. Our labels were continuous, right? Now we'll do some classification using KNN. We covered it last class. Yes, so KNN. For KNN, first we will load our data set. I'm using Seaborn for that. So let me. Yeah. So Seaborn is a Python package. It offers some data sets, some visualization tools. So I'm using it and loading a data set. And you later on you can play around with it by yourself. You just need to specify the data set's name. Here I'm using Iris dataset. So again, I mean, it's the same. First, you want to get to know your data, right? So always print the head like first 5 rows, then describe it. So print out the summary statistics, and then find null values, the missing values, right? And after that, let's run it, and then looking at this, what data preprocessing we could use here? Oh, also this. Right now, we don't really have any outliers. Last time we said outliers. We don't really have any outliers. Oh, first of all, why do we have 4 different graphs?
4 features.
Yes. So we're just comparing, because we cannot just visualize and make it 4-dimensional, right? Our brain doesn't work this way. So we have to do it like this. It's called parplot. And Seaborn, I mean, has really nice features to do so. Yeah, so there are no outliers. There are no missing values, right? I mean, everything looks perfect, but remember, what model are we building here? We're building KNN, right? And for KNN, it's really important to normalize your features, right? So here, I mean, if we don't normalize, how KNN works, basically it finds distances, and based on this, it tries to guess which label it belongs to, right? Like 3 closest points, or so here we have 4 features. So sepal length, sepal width, petal length, petal width. And here, if we don't normalize it, if we don't put it on the same scale, your model will think, okay, petal width is way less important than, let's say, sepal length. I mean, which is not true, right? I mean, you could measure petal width in millimeters, and then it would be huge. So you always want to normalize it. And how do you normalize it? One way to do so is you take your point and then minus mean, and then divided by standard deviation, right? So we'll do that. So the only data preprocessing, I mean, it's a clean data set from Seaborn, but we'll do data preprocessing. We will normalize it. So yeah, first of all, I have a question. Here we're splitting our data set into training, validation, and testing. And if you remember, in linear regression, we didn't do that. Why is that? Why we have a validation? Why do we even need that validation set here? And we didn't need it in the linear regression, in ordinary least square regression. Because of hyperparameters, right? We have hyperparameters here, and before we didn't have any hyperparameters. So what's the difference? In linear regression, you have just parameters. Parameters, you can learn them by using gradient descent or some optimizing algorithm. I mean, you have a mathematical loss function or mathematical formula, let's say, and then you optimize it by finding derivatives, setting it equal to 0, or like some other optimizer, and then you can, I mean, your model will learn it itself, right? But then if you don't have this, sometimes you cannot do that, and it's called hyperparameters. What you can do with it? I mean, there are many techniques for that, but then you can use grid search. What is grid search? So first of all, first rule of machine learning, right? Do not look at your test set. So we cannot use our test set. We split out. Now we have our train set. We have to split our train set into train and then validation set, right? So we will use grid search. We will set a value for our hyperparameter, train it, and then test it on the validation set, because we cannot test it on the test set. We cannot look at it until our models are ready. So we will put a value for a hyperparameter, build that model, and then see its performance on the validation set. and we will do it for different values. That's called grid search. So basically you specify some values, you put them on the train sets, hyperparameters, you build a model, and then test it on the validation set. You see, linear regression doesn't have any hyperparameters. It has just parameters, and you can learn it by using gradient descent. But KNN only has hyperparameter. It doesn't have any. It doesn't have any parameter. Yes, so they call it lazy learning. So KNN is just, you know, it learns when you ask it to learn. When you ask it to predict some point, it starts learning, and it only uses hyperparameter. It just asks you, how many neighbors do I have to look at? And you don't know how many is good, so you just try different values on a train set, test it on the validation set, and then you choose your hyperparameter. After that, you combine two sets, you use that hyperparameter, build a model, and then test it on the test set. And that's it. You don't do anything else after you test it on the test set. Yes, so now let's do this. Let's do this. Yeah, so first of all, we can again split it into train and validation tests. We can again split it, but then we have to do it in two steps. Because we have three sets this time, right? So now we can split it into train and then validation test set. I mean, we could split it into train, validation, and then test set. I mean, it doesn't matter which way you go, right? I mean, as long as you end up with 3 different sets, you are good. So as a next step, we will split it into validation test, and then you already had the train set, right? And then we will use that scalar function from scikit, standard scalar. So it just normalizes your features, the same thing we talk about. But I have a question. So there are 2 ways you can go about it, right? First you can normalize everything, and then split it into different sets. Yeah.
Does the value of the hyperparameter depend on anything?
What do you mean?
So we have to give certain values for the hyperparameters for the grid search.
Yes.
So does it depend on any of our data, or what value we should?
No, normally you don't know. But I mean, if there is, I mean, because in KNN it's easy, right? You can try 3. Normally you don't try even numbers 2, because I mean it can be, you know, tie. But then you try 3, 5, 7. But then for some problems they have, like, for example, 3 models. Some 3 models they have 10 hyperparameters. And how do you go about it? Like, how do you know which values to try? You go to some related literature. I mean, they've been testing this, and then, you know, find some similar problem, and then try out these values. If not, just try out hundreds of values. It will take a long time. Really, I've been building some models, and some models take days to train.
So it's entirely random number.
I mean, if you go random about it, you can go random about it. It will take really long time for you. You see, I mean, if you don't, and we'll see why. We'll see why, and we'll see how to choose it. But then what I was asking is that you can split your data into train, validation, test, and then normalize, or the other way around. Which one do you guys think is good? Like, which one should we do? Should we preprocess our data and then split, or split and then preprocess?
Split and then preprocess.
Yeah, why is that?
So there may be.
Yeah, so that's right. That's correct. What you said. No, first split, then preprocess. Why? So let's say I mean, number 1 rule was do not look at test set, right? And then many modelers do this mistake. Let's say you first preprocess it, but then you are using this test set's information, right? Now your train set has some information about general distribution of your data in test set, which it shouldn't know, right? It's like someone is going to an exam and you are giving him hints. And then you say, okay, he did really well, but then you don't know, right? You already gave him. It doesn't change a lot, but then it slightly improves. I mean, normally in practice, as I've seen, so you don't want to do that. First, you want to split it, and then, yes. So, and also, first we split it, and then now we're normalizing only our train set using train sets standard deviation and train sets mean, right? And then we're transforming it, and you can later on you can play with this, you know, code. Yes. So now what we're doing is we are we are specifying values for our k. So numpy arrange. So we're using numpy arrange. It will just put values like 1, 2, 3, 4, 5 till 16. So it doesn't include the last value. And then we will be storing our accuracy values in this list. We'll be just appending it to it. And then we're saying for k and k. So that's the k, right? So it will try each k value. We are building a model. So we're specifying this is our model. It's k neighbors classifier with k equal to k. So it will be 1, 2, 1, 2, 1, 3. So basically this 2 means each other, like it tries 1, 3, yeah. So then we'll be fitting it using train set, and we'll be predicting it on the on the validation set, right? And then we'll be appending that accuracy score. So you guys understood what we're doing, right? And now we can, why we need that? We just need this list, validation accuracy list. We can plot this list now. And basically, that's just matplotlib. You can look at it by yourself. That's our result. That's what we have here. We want our accuracy to be as high as possible, right? And which one would we choose? Which one do we choose?
Is 11.
Yes, k is 11, right?
Yeah.
Yeah, so this is what we did, right? We trained on the test set, so the performance on the validation set. And now we say, okay, k 11, it's the best. K, it doesn't overfit, doesn't fit, it's doing pretty well. But now we have so many models, right? We need to retrain our models again. So what we do here, we put back validation and train set together, train it on 11, right? We want as much data as possible to train. So we put it back. We're using this pandas concat function.
So, excuse me. So we are using validation set just to get the k.
Yes,
Okay.
only that.
Okay.
Because you cannot, you cannot use test set for that. In real life, for example, if you don't have much data, you can use sometimes they just don't have test set, right? And then let's say your manager told you, okay, build a model, and then in a month you have to deploy it no matter what, and you don't have enough data. You can build it and then test it on the real life environments, but then you just don't have test set. This rarely happens. But then if you anyways have to deploy it, right, and you cannot validate on the test set, there is no use for your test set. So you can do that. Rarely I've seen that being done, but yes. So validation test only to get hyperparameters. This is why we didn't have any validation set in the ordinary list scores. Yes, and here. Yes. So yeah, I just want to mention that some types of linear regression have hyperparameters, right? Like if you penalize it. But this is more advanced, just for you to know. Later on, you don't say just linear regression doesn't have any hyperparameters. Ordinary least square regression, linear regression doesn't have any hyperparameters. But then some types of it, like when you penalize it, they will have hyperparameters. Yes. So, anyways, we put train and validation sets back together. We print their shapes just to make sure. Now again, so what we're doing here is, for example, now. Another question. We normalized using mean of train set and standard deviation of train set, right? And then we built a model based on this. And now your model knows only one thing. Let's say your mean was 5 and then standard deviation was 2, right? Now your model knows that, okay, you have a data set, and then if you subtract 5 divided by 2 and you build a model based on this, I know how to predict this, right? You get my point. So now you have to use to normalize, let's say, validation set or test set. You have to use train sets, standard deviation and mean, because it was trained on that, right? Your model knows that, like, okay, if you take minus this value and then divide by this value and you build a model, I know how to predict it. Because some people make a mistake when they normalize, let's say, test set. They will normalize it using test sets mean and standard deviation. This is not what you want to do. You guys understand it, right? Yeah. So now we're so we're fitting it using okay. We again defined scalar, right? And then we're normalizing using train validation sets. because we'll build another model, right? So first we're doing this train validation sets, subtracting mean and dividing by standard deviation of train validation set, and then transforming this set, okay? But then we're also transforming X test. But then if you see that we're using it, the scalar, and scalar was already that, you know, that train validation sets mean and standard deviation. Yeah, so basically it's doing what I'm saying right here. And then we're building another model, KNN, with 11 neighbors. We're fitting in on the train validation set and then predicting on the X test. And X test is already normalized. If you look at here, using standard deviation and mean of train validation set, right? It makes sense, right? Yes. So, and then we can do that. We can run. Oh, I didn't run everything. Oh, I didn't. Okay, let's run everything. Realized I was not running cells. Just to see. It will take a while because it's running each cell. Let's see, this is done. Yeah, and you see, because we used this random state 100, I mean, it's still random, but results are the same. Each point is the same. So it's just to be able to repeat these random numbers, you know. Yes, so it's ready now. The final result here, what's the final result? The accuracy of the final model on the test set is 0.93. So it was 93% accurate, which is pretty good. Yes. So now we covered what? We covered supervised learning, linear regression.
Okay.
Yeah, this is regression. And then we covered KNN. This is also supervised learning, but classification. Now, I mean, we didn't cover this in class, and now, I mean, we still have some time left, so we can talk about it. So we can cover unsupervised learning. Unsupervised learning using k-means. So basically, I mean, who knows about unsupervised learning and how k-means works? Does anyone know how it works? Or I know some data science students here. I mean, they covered it last semester, but yeah, do you know or no, right? So basically, in unsupervised learning, you don't tell what your Y's are, what your labels are. And there are several things you can do if you don't know your labels. And one of it is called clustering. So basically, let's say you have points like this. You have a point, right? And this is a point, right? And that's your data set. And let's say, I mean, this is some x1, that's some x2. And then you said, I mean, you didn't say that's some label and that's some label, but then if you run k-means, it will tell you, okay, that's cluster 1 and cluster 2. You have to specify how many clusters you want. So if you do that, it will say, okay, that's cluster 1, that's cluster 2. You see, it will call all of these like 0, 0, 0, 0, 0, and then this like 1, 1, 1, 1, 1. But then if you do like, if you tell that you want 3 clusters, let's say if you tell it that you want 3 clusters, and the same here, it might do something like this, and then this. You see, you just tell it how many clusters you want, and then you just cluster it based on how close points are. I mean, it's not hard, right? And then each cluster has what? It has a center, right? Center point. Each cluster has a center point. So everything you need to know to understand this example is that unsupervised learning, you don't give labels. And if you're clustering, you specify how many clusters you want, and it will just cluster those points into that many categories, and it will have that many center points, right? And normally, I'll tell you, in real life, they almost don't use unsupervised learning for production environments. Like there are many more useful cases of unsupervised learning than supervised learning. So I wanted to show you something useful that can be done with unsupervised learning here. Yeah, so, and we will be doing some image preprocessing here. So we have that image. Let's load it. So let me show you. One sec. Okay, we have this image, right, of a husky dog. So for an image, what are the feature? What are axes? What axes are? Do you guys know?
Pixels.
Yeah, but not just pixels. So for each color, I mean, do you know if you mix two colors together, you will get a new color?
Yeah.
So the theory is that if you mix red, green, blue, you can get whatever color you want, like not whatever, but then whatever you can see with your eyes. And normally they specify, so how many? Yes, so, so they're using 0. So here, if you have a picture, you choose a pixel, and then for each pixel, you will have a red, green, blue, RGB. And then each, for R can be from, let's say 125. This can be 256, right? I think they're going to 255. Yeah, 255. So each of them will have a value from 0 to 250. Yeah. So your samples, actually, your observations are picture because you have many pictures. And the features are RGB of each pixel. So it can be R of pixel 1, G of pixel 1, or G or B, for example, of pixel 50. So you have many pixels. So each feature will be whether it's pixel 1 or 100, and then each and also whether it's RGB and like value, intensity value of RGB, right? So we have this picture. We can load it using matplotlib. Matplot is great for that. So we're just loading it using matplotlib. And then we need to check its size, right? If you do size, I mean, we're storing this picture, one picture, we're storing this picture as a data set. Original image is our data set. We're loading it using matplotlib. And then we're just visualizing it. And after that, we're just, seeing its shape. So it's 256, 256, 3. 3 is RGB. I mean, it can be more or less. If it's like gray picture, gray, like black. Yeah, so it will only have 1. Yes. So and then there are 256 multiplied by 256 pixels. So let's go on. So now also it's the same thing. We want to always k-means, KNN. We always want to normalize our data for the same reasons. We don't want to say, okay, our red intensity is very important and then blue is not important, because that's just not true, right? So first of all, we took our data set and then we standardize it, right? And when I saved it using matplotlib, it already saves it as like in this format, is a matrix format, right? Which has like, this is pixel 1, pixel 2, and then this is like red of pixel 1, green of pixel 1, right? Blue of pixel 1. So you don't need to do anything with it. You just load it with matplotlib and it will load like this as a matrix. Is it clear? Yes, right? Yeah, so now we normalized our data set, which is just a matrix now. It's nothing but matrix. And now we can just run our model because, I mean, it's pretty clean. There are no missing values, nothing missing. So, and now what we want to do, our goal here is, so basically why we're even doing that? What are we doing even here? So basically, we have a picture and it has thousands and thousands of colors, right? Many, many colors. I mean, it weighs a lot. Like you have to store these colors. But then what you can do is you can cluster it in, let's say, 16 points. We are here clustering it into 16 points and then replacing each color with cluster mean. So replacing it with mean value of this cluster, and then we can store image not with 1000 colors, but then with 16 colors. And then we can store these colors in a dictionary, in a hash map, and then just say, okay, these are the points, 16 points. And for each pixel, we will say, okay, it's this, color and this color, and it will be very efficient. Like we will only store it with 16 values. We'll just store the index of a hash map there, and we will just access for each pixel that index when we'll be rebuilding the picture. You'll see, it will make sense. Okay, now we have this normalized data set. We'll cluster it into 16 points, right? So for that, first, always you initiate a a model. So here we're initiating a k-means with random state clusters, random state 0, and then we're fitting it using the image itself because we don't have any labels. And also we're getting centers, right? Centers is what we want. We want to replace each pixel's color with its center's color, right? So it will have 16 colors. So let's run it. Okay. So now look, how many? I mean, originally we had 20. Yeah, so originally, I mean, you can read about this later, but then originally our picture was represented with 1.5 million bits. And now we're representing it with like 260,000 bits. So, I mean, it's very efficient. And now we're assigning the centroid colors to each point, right? So each point we're saying, okay, I mean, we're replacing with this centroid's value. And you will see why. So now let's just compare it. Like, what did we get? So that's left picture is original picture, and the picture in the right is compressed with 16 colors. You can see, I mean, it's not perfect, but then it's close enough, right? Yeah. So this is how k-means can be used for something, or clustering can be used for something useful. Like it's called unsupervised image compression. Here, you don't have any whys. You're just saying what value should a pixel be replaced with, right? Yeah. So do you guys have any questions?
So these 16 colors are the dominant ones they choose?
Yeah. So basically, as I said, you can call it dominant. So basically, these are the centroids. So because I mean, for image, you have pixel, as I said, and then pixel will be like this, right? So you have this and then this. And these are like pixel of red, pixel of green, pixel of blue. And then this is one color, right? And then this is another color, and it will be totally different. It's very unlikely that these two colors will be the same. And then you have to, somewhere else, you have to store, okay, if it's 0, 0, 1, it's one color, like, and then if it's, and then you have to store a lot of colors, but then you want to store only 16 colors. That's what you basically are doing. You have to store, I mean, this combination should be stored somewhere, right? Yes, so what you are doing here is basically finding 16 colors that can represent your picture in a best and most efficient way by clustering it into 16 colors, and then finding their center points, like center. So it's just fair to each color in that region, and then you are replacing each pixel's color with with that color with its corresponding cluster mean, and I mean the result is pretty. I think it's impressive, right? I mean, it's not bad. I mean, you can see that it's compressed, but it's like many times more. It weighs less than the original image. Yeah, so basically, this is how k-means can be used to cluster, and it can be used to compress images. Do you guys have any questions?
Is this something related to 2 raised to power also? Like
What?
16 colors, compressed with 16 colors. So is it something related to the like 2 raised to power 4 or something like that?
Yes. So why we chose 16, right?
Yeah.
So I mean, you can read about it here also, but then so it can be represented with 4 bits per pixel, right? I mean, just how bits works, like how many different values you can store in a bit. So that's why we chose 16. I mean, you could choose something else. It would be just more bits. Yeah.
But 2 raised to power.
Yes. Yeah. I mean, that's how computer science works, right? Everything is to the power of 2 for some reason. But yes, this is how. I mean, it just can be stored more efficiently if you do 16. If you could do something else, it doesn't matter. You could just do twice as less. You could do not 125, not 255, but then 255 by 2, you know, in the flow rate. Yeah, so basically that's, you know, and if you read about it, I mean, these are three practical implications of machine learning, like unsupervised and unsupervised. Just read about it, and you know, and really important thing I want to mention, go back, the data leakage. Many even experienced machine learning engineers do that mistake, that you know they preprocess then split. You don't want to do that. You just want to make sure that you have that set that's never been used before, so that you could predict on it and then say, okay, my model is doing well or not. So just keep it not touched, and this is what we did. But sometimes it's like, okay, I didn't train on it, but you also preprocess on it, right? Don't do that. Even and we only talk about normalization, but sometimes you also use it for imputation. Do you guys know how imputation works? So I mean, you can use KNN for imputation. It's not always classification. So basically, let's say you have one. Let's say you have 1, 1, and then 3, and then this value is missing, right? How you can, I mean, you can drop this row.
Or getting the average.
Yeah, I mean, no, this is wrong, because it should be a one variable, right? That's variable 1, variable 2, and then this is 1, 1, 0, 3. This one is, you don't know. And how can you, you know, what can you do about it? I mean, you can just drop this row, or you can try to impute it. I mean, there are so many techniques. You can just take mean of it, and say this. Or you can say, okay, I will look at 3 closest points just in KNN and take their mean. Or I'll take their mode, like whichever is the largest value, I'll just impute it with that. So, but then if you know, didn't split it yet, you are still using test set, you'll be using test set's value to impute, right? And this is, you don't want to do that. You want to split and then impute them separately. And this is like a whole other problem. Yeah, so just make sure that you don't do any data leakage, because let's say your test performance was really good, then you want back, and then you know you're testing it in production in real life, and it will be doing worse, because in real life you'll not be giving it any hints. Yeah, so this was it. That's it, I guess. Yeah. So anyways, it was a pleasure giving a lecture today. So guys, see you next time.
Thank you.